Counter EMF is the voltage induced into a coil as it rotates in the magnetic field. As a coil spins in a magnetic field, the voltage is induced into the coil. The induced voltage opposes the applied voltage from the drive. Counter EMF is proportional to the strength of the magnetic field and the speed of the rotating coil. The flux varies as the coil rotates in the magnetic field. It's strongest when the coils are perpendicular to the lines of force. There's no counter EMF when the coil is moving parallel to the line of force. The coil is moving parallel to the magnetic lines of force at the point of commutation. There must be no counter EMF induced into a coil that is under commutation. If it is present at the point of commutation, there will be arcing at the brush. As speed increases, so does the counter EMF voltage. A coil spinning faster produces more back EMF. Less flux will produce less counter EMF. With a DC motor, speed is self-regulating. When current flows in a DC motor armature and the armature rotates, there'll be an induced voltage developed in the armature coils. Also, there will be a voltage drop across the armature windings due to the resistance of the armature coil. And finally, a slight voltage drop across the brushes. All of these voltages oppose the applied voltage, and the speed of the motor is satisfied when the sum of these three voltages equal the applied voltage. This is how the speed of a motor is self-regulating. If we increase applied voltage, the motor will speed up until the equation is balanced. Let's discuss what happens when the applied voltage is increased. The difference between the voltage applied and the counter EMF is greater. This increases current in the armature and increases applied torque. Increase in supplied torque versus load torque, so the motor will speed up, and the increased speed of the motor raises the counter EMF. And counter EMF increases as speed increases until the equation is balanced. What happens when the applied armature voltage is decreased? The difference between applied voltage and counter EMF is less. This decreases current in armature and decreases the applied torque. Decrease in supplied torque versus load torque, so that motor is going to slow down. The decreased speed of the motor decreases counter EMF, and counter EMF decreases as speed decreases until the equation is balanced. What happens when the applied load of the motor is increased? Increase in load torque versus supply torque, so the motor slows down. The decreased speed of the motor decreases counter EMF. The difference between applied voltage and counter EMF is now greater. This increases current in the armature and increases supplied torque. An increase in supplied torque versus load torque, so the motor speeds up. This increased speed of the motor raises counter EMF, and counter EMF increases as speed increases until the equation is balanced. And one more, what happens when the applied load of the motor decreases? A decrease in load torque versus supply torque, so the motor speeds up. And this increase in speed increases the counter EMF. The difference between applied voltage and counter EMF is now less. This decreases current in armature and decreases supplied torque. Decrease in supplied torque versus load torque, so the motor is going to slow down. The decreased speed of the motor lowers the counter EMF, and counter EMF decreases as speed decreases until the equation is balanced. We said when load increases, the motor would temporarily slow down until the increase in armature current and torque output brought the motor back to speed. But does it actually recover all the way? The answer is no. It will not recover all the speed all the way without increasing the applied voltage. A load increase will result in the armature drop increasing somewhat. Therefore, the equation to be balanced, the counter EMF, must be slightly lower than before. What actually happens is the armature current will increase to support the torque demand. When this happens, the armature current will be higher than before the load change. So will the IR drop. And based on this, IR drop is now a larger portion of the total sum. So we can see in this animation that the armature drop portion increasing slightly makes the counter EMF portion decrease somewhat because the applied voltage stays the same. And again, with more load increase, the same thing happens. If we need precise speed control, a motor should be configured with the tachometer and the drive set to regulate the speed. A DC motor has a percent speed regulation characteristic. It's equal to the no load speed minus the full load speed divided by full load speed times 100. The speed regulation relates to the resistance of the armatures somewhat, and the lower armature resistance, the better the speed regulation will be. There are three DC motor types that we'll discuss in more detail later, but for now, here are some differences in their speed regulation. The DC shunt motor has about a 10 to 15% regulation. A DC series motor has up to 35%. And a DC cumulative compound, depends on the compound type, can have somewhere between the 15% and the 35% speed regulation. The speed regulation of a DC cumulative compound motor is superior to that of a DC series motor and inferior to the DC shunt motor.